You see this shape, the bell curve, and you think, yeah, I know that. We all learned about it in school. It feels familiar, safe even. But what if I told you that everything you assume about this curve is just scratching the surface? So, in this explainer, we're going to decode the actual blueprint of the bell curve. We are going under the hood to figure out not just how it works, but why this one shape is so unbelievably common, and why that can be both a huge advantage and a really dangerous trap. Okay, let's just dive right in. Your statistics class, it showed you the shape, right? But it probably skipped the most important part, the why. There is a fundamental secret to the Gaussian, a reason for its power that most textbooks just gloss over. To really get it, we can't just admire the shape. We have to look at its genetic code. What is the actual mathematical DNA that forces something to become a bell curve? The answer, it turns out, is shockingly simple, and it changes absolutely everything. You see, the real secret isn't in the curve itself. It's in the blueprint that builds it out of randomness. And that blueprint is defined by one super powerful mathematical idea. And that idea is moments. Now, don't let the word scare you. Seriously, just think of moments as a distribution's DNA. They're a series of numbers that describe every single thing about its shape. Where it's centered, how wide it is, if it's tilted, how pointy it is, the whole shebang. And here's where it gets kind of wild. The Gaussian's DNA is just incredibly simple. All of its odd moments, the third, fifth, seventh, you name it, they're all just zero. Boom. That's what gives it that perfect symmetry. And all the even moments, they follow this one single elegant formula that's driven entirely by the variance, sigma squared, which leads to this absolutely profound conclusion. You only need one number, the variance, to define the entire infinite chain of a Gaussian's moments. If you know the variance, you know everything. There are no other secret settings or hidden knobs to turn, just one. So what's that weird double factorial thing in the formula even mean? Well, it's just a shorthand for counting all the ways you can pair things up. And that is the secret. Gaussian randomness has no complicated hidden structures, no secret conspiracies between 3 or 4 points. It all just boils down to simple pairs. Everything else, it's just variance.
Okay, so if the Gaussian is that simple, why do we see it everywhere? This incredible simplicity is the key, and the reason lies in the central limit theorem, which honestly is best explained with a fantastic metaphor.
Think of the central limit theorem as a giant washing machine for randomness. It takes all these different, messy, complicated types of randomness and just cleans them up. Here's how the wash cycle works. You throw a bunch of totally different, independent, random things into the machine. As you add them all up, all their unique, complex features, their higher-order moments, their special quirks, they just get washed away. They cancel each other out in the mix. The only thing that reliably survives is the simplest structure of all, variance. And what comes out at the end? A perfectly clean, simple bell curve. This leads to another perfect analogy. You can think of the Gaussian as the JPEG of uncertainty. You know how a JPEG file compresses a rich, detailed photo by throwing away the super fine details you might not notice? Well, the central limit theorem does the same thing to randomness. It creates a Gaussian by throwing away all the complex, detailed information. It's a lossy, simplified summary of reality. And this is exactly why machine learning is totally addicted to Gaussians. Look at all these methods. From least squares to Kalman filters and beyond, they all lean on the Gaussian assumption because it makes uncertainty obedient. It's clean, it's easy, and you only need that one parameter, variance, to control it. But, and this is a really big but, this beautiful simplicity hides a very dangerous trap. Because when you rely on this clean, compressed model of the world, you can set yourself up for catastrophic failure. It gives us this totally false sense of security. It makes the wild, chaotic randomness of the real world feel tame, manageable, and predictable. But here's the problem. The real world isn't clean at all. A Gaussian model, by its very DNA, dramatically underestimates the chances of extreme events. Real-world data often has what we call fat tails, where shocking black swan events are way more common than the nice, tidy bell curve would ever lead you to believe. And that is the trap. A model built on a Gaussian assumption can look perfect 99.9% of the time. It tracks reality beautifully. It looks fine. Until, all of a sudden, it isn't. And when a real-world shock hits, the model is completely blindsided, leading to these massive, overconfident mistakes. So this brings us to a crucial final point. That simple formula for the moments we talked about, it isn't just a handy description of the Gaussian. It's a unique, undeniable fingerprint. Think of it like a test. If you take any random distribution out there and you calculate its moments, and they happen to match that simple Gaussian formula, well then, it has to be a Gaussian, period. No exceptions. No other distribution in the universe can fake this DNA. It is a mathematical certainty. And that leads us to this final, really radical idea. The bell curve isn't nature's favorite shape. It's not a sign of perfect, elegant order. It is the exact opposite. It's the wreckage. It's what's left over after unique, complex, interesting information gets systematically destroyed. This really is the core takeaway. Seeing a bell curve in your data isn't a discovery of some deep natural law. It's a sign that the randomness washing machine has been at work and you've washed away all the interesting structure. The bell curve is the ghost of lost information. Which leaves us with one last critical question. In a world full of stock market crashes, climate change, and complex systems, where the extreme events and hidden structures are the things that matter most, what happens when we can't afford to throw that information away? What do we do when we have to face the messy, non-Gaussian truth of the world?